So let's actually complete the question. So next question was essentially around this is a word transformation, right? So let's get to the word transformation now. So word transformation is like this question is essentially you are given a dictionary of words, all the words in the dictionary is given to you, and your goal is essentially to convert from a given word, which is like cow, to bat. Okay, and you're only permitted to make one change, one letter change at a time. So a cow can actually become cot. Okay, that's because you've replaced a W with a T. A cot can become a cat, and a cat can become a bat. So what changed is the O, what changed is the C. Okay? Right?
And we want to do with the minimum.
The goal is to actually find a answer.
Okay.
Find one solution is what the question is. But we would prefer to do it in the minimum number of transformations. That is one thing. Right? And the thing is every word in between has to also be valid English words. Another way of looking at this was essentially probably cow can end up becoming bow, right? And bow can end up becoming bot. Bot can become bat as well, right? So there are multiple answers, and there are multiple equivalent answers as well.
So what to A, that kind of jump available?
Which one?
It's not like only next character should come in, not like.
It's not next character. Only one letter has to change. So from cow, what changed to become bow? The B changed, right?
Okay.
From bow, what changed to bot? The W changed.
Okay.
From bot, what changed to bat was the O.
Oh.
Only one letter can be changed, but the letter can be changed to anything.
Okay.
As long as it's a legal English word.
Okay.
Okay? So now if I ask you to build this is called like a word, this is like a word transform puzzle, right? So how do you go about solving for this? Any questions before we go on? Is the question clear?
So there is no, we can't add or remove, right? So if it's a three-letter word, it will end up becoming three.
Correct. So in this question, yes, it says it's a three-letter word will remain three-letter words and it only transform through existing three-letter words alone.
Okay.
I can easily come up with an interview question where I can say that you are permitted to add or delete letters too.
Mm-hmm.
Right? I can actually say that cow can actually become crow, for example. And crow can become something, and then you can delete a letter, you can add a letter. I can do that I can, as an interviewer, I have the power to say, yes, you can do this. This question specifically limits in the space. So let's pretend that the question is the question. But those additional complexities may or may not actually change the complexity of the answer that you're trying to get to. Okay, so how do you go about solving this? Anyone has actually seen this question, like solved this question before? Just trying to see if you have. Doesn't look like it. Go ahead. You had a question.
How did you come up in the first place with cow?
Cow was it's given. Cow was given. Bat is given.
Okay.
So essentially, the input goes like essentially it's transform like cow to bat. Give it the dictionary. That's how it's given to you. You're given an array of words which are like legal words. So. What is the class of words?
If we know,
backtrack.
It's a
Hang in there for a
graph
second.
problem.
Is it a graph problem? Does it look like a graph problem?
I can
Maybe.
transform it to graph problem and find the minimum distance between the 2 points.
So clearly, even though the question in some scenarios the interviewer might actually mislead you by saying that find some answer, doesn't matter if it's the shortest path or not, it's okay. But finding the shortest path seems to make the logical sense. It doesn't make sense. For example, for me to go from, if I have to go from like cow to cot, right? I can go take an entire big detour. I can do this, right? Cow to bow, bow to bot, bot to bat, bat to cat, and cat to cot. I can do that too, theoretically. But it doesn't help. So even if the interviewer is not saying that get me the shortest path, some of the things here logically it sounds like a shortest path is the right answer. To find the shortest path, I would not use backtracking. Instead, I would use a breadth first search. And so this looks like a graph problem to us. What are the vertices and what are the edges in this graph?
So each number are vertices.
Each word.
Vertex.
Oh, what?
Each word, right?
Yeah.
So cow is a vertex.
Yeah.
Okay, and
anything it can change to that is basically connected by one distance.
Anything cow can change to, which is
Valid
essentially
word.
like a cart,
Yeah.
bow, okay, maybe car,
Yeah.
or maybe like low, whatever those words are. They're like exchanges, and those are all valid words, right? Okay, so
Is
that's
dictionary combination of this word or is dictionary a set of characters?
dictionary is just a set of characters.
Oh, just a set of characters.
No, and a set of
Set of
words.
words.
It's a dictionary is a hash of words,
Okay.
and you can just iterate through the dictionary if you want. So essentially, what you need to do is you need to iterate through the dictionary, and obviously you can discard all the non-3-letter words because obviously cow cannot be a neighbor to a 4-letter word based on current rule. You can discard everything else, and then what you're trying to do is now you're trying to figure out if the given word is actually a neighbor of cow. If the word is bought and cow, since it varies in 2 locations, it's not a neighbor. So you can just iterate through the entire thing and find out all the neighbors. Once you have found all the neighbors of this, you can again continue. Is this edge bidirectional or unidirectional?
It's bidirectional.
Actually,
Right? If
Yes.
bow is actually a neighbor of cow, then cow is a neighbor of bow as well, right? We know that. So one of the ways you can actually avoid that is by once you've processed a word, you can delete it from the dictionary, right? So you don't have to keep reprocessing it. So you're done with this. Once you have figured out this thing, it's a graph. In this graph, you just do a simple breadth first search with standard marking so that you know that you're not revisiting that again. So cow is a neighbor of bow, bow is a neighbor of cow. So you don't want to go back from bow to
What
cow.
is the technique to find the neighbors? Like,
I would just iterate to the entire array. There's no other good way. The entire list, and figure out if there's a how do you find out?
your n square? Right now you are going through.
It is n square. For every word, I'm trying to find out if every word is a word of is a friend of that. That's what I would do, unless there is a better way of doing it. Is there a better way of actually figuring out if a word is its neighbor or not?
One way you can do it is for each character location,
Mhm.
you can try changing it to a different character.
Mhm.
And then you can check if this word exists in the dictionary.
So the list of possible neighbors for given a 3-letter word, the list of possible neighbors is essentially there are 25 replacements you can do for this, 25 replacements for this, and 25 replacements for this. So by 25 times 25 times 25 are the possible neighbors for this. Now you can go iterate through each one of those neighbors and then go look it up in the dictionary to see if that is actually a valid word or not. You can do that. For 3 letters it makes sense, but for beyond that it actually becomes a little bit of a crapshoot. If you have your dictionary as a trie,
Correct.
not a hash map, then you can do a little better. Because if no word starts with X in your dictionary, then you don't even have to try that many letters. No word starts with XP, then you don't have to try all the other combinations. So you can do a lot more pruning or finding neighbors if you can do that. So just the problem of finding neighbors in and of itself is a problem solving question which can actually be, the interviewer can take you down the depth. So this is what happens in most interviews. Just because you know the answer to a question or just because you've solved it does not mean that you get much of a leg up, because what happens is you know how to solve this BFS, I know how to write BFS code, it's like the back of my hand, and then the interviewer is going to take you down this path of figuring out what's the most efficient way to generate neighbors, and you may or may not have done that. So absolutely, this is a pretty good technique. It's constant time primarily because it's 25 times 25 times 25. But what if it is 10 letters, 20 letters? Then it's 25 power 10, 25 power 20. It becomes larger and larger. And as it becomes much larger, you might want to use a trie to minimize that.
But if this logic we can come up with some efficient way, then we can use this logic itself to find the answer itself, right? Efficient way of finding the neighbor. To find the neighbor only we are going for breadth first and creating graph and all, right? If this finding the neighbor logic, if we come up with some clean logic by using that logic itself, we can find the actual answer also, right?
Well, I mean, at the end of the day, it is the same process. You don't have to build the whole graph. Because essentially what you can do is recursively of such. The
Yes.
problem with this is it'll end up being a...
Yeah, complex size it will be,
No,
maybe, but still if this logic is, if we are confident it's really efficient, we can reuse this logic for finding the final answer also.
Correct. So essentially what you're trying to do is that you're trying to say that given a word, you're trying to find all neighbors.
Neighbors.
Then you take all the neighbors and then you put it in the queue.
Yes.
Okay?
Something.
Then
Yeah.
you dequeue the first element and then you find all neighbors.
Yes.
And then you enqueue that and then you
Yes.
take the second one from the queue and then find all neighbors and enqueue. That's what you're trying.
Yes.
That's what you're trying to do.
Yes.
So you don't have to construct the graph
Yes.
at all. And
Yes.
this find all neighbors itself is more than enough, because the graph is just it's a notional graph at that point of time. Okay? So this makes sense. Now if I change the question a little bit, to say, I'll come back to it. If I change the question to say that, you know what, addition is permitted. So crow is okay. Cow can become crow. Like adding one letter anywhere in the word is allowed. Or cow can become cows. Right? So then what? No big difference.
Yes.
Then the neighbor
Will be-
philosophy, the mechanics that govern what is a neighbor has just changed. That's all.
Yeah.
The logic doesn't change at the end of this. So essentially, what I'm saying is that these rules are just arbitrary rules to strip you out. So if I were to say that you can only from the other way I've seen is that essentially saying from vowels you can only change to vowels, from consonants you can only change to consonants. Now go fish, right? No big difference. At the end of the day, all you're doing is you're just changing the rules of what governs this, right? You may add any number of like random things here. You can actually one of the transformations is that essentially saying that you can only go up but you cannot go down, or you can only go down but not up. So which means that once I go from COT to CAT, now I'm only limited to reducing letters. I can't go up. So from CAT I can go to BAT because CB, right? B is less than C. That's okay. But I can't from CAT I can't go to like XAT or PAT or something because it's like that. So those are all like just stupid variations, and there is no meaning to those things. Those are just complexities just thrown in there, which really doesn't add to the problem space or anything. Okay. So your question.
Yeah. So if we don't construct the graph, then we have to still figure out that we are not coming back to the same.
How do you figure that out?
No, if you don't construct the graph, then put it in the dictionary and figure out, or how? Because if you don't want to construct the graph and then just keep going, then we might end up coming.
You just remove it from the dictionary. You'll never come back.
If we remove from the dictionary, okay.
At the end of the day, you're actually doing enumeration, which is essentially this 25 combination.
I see.
And then enumeration, and then you check in the dictionary. Only if it's in the dictionary, you're putting it in the queue. Right? Once you have taken it from the dictionary and put it in the queue, eliminate it from the dictionary. But it's a good call out. I mean, I missed that in the first go around. So the problem is that once I'm with cow, I go back to bow, and then I'll come back to cow. Right? When I'm looking for neighbors of bow, cow is going to be a neighbor of bow. So what do? I need to figure out how to make sure that I don't go back from bow to cow. And since it's not a graph in the way we are looking at it earlier, where you can't put your footprints and then figure out the breadth first in weird ways, it becomes harder.
But even in graph also we will store this information in some extra thing like I already visited, something like that, right?
So you, instead of doing the visited elements, you can actually just remove it from the dictionary, and then that essentially you'll never come back to cow because cow is no longer a valid word.
Right.
Okay.
That is another way of doing it. But yeah, you can also keep a set of visited words, and eventually, if that might be as big as a dictionary. That's all. So you'll say it is in the dictionary but not in the set of visited words. Then you have to do that. You can do that as well. That might work. Any questions with this specific one?
I mean, if we remove if we work on bow, we also need to remove bow, but we need to put it back if we move to COT, right?
Why? If an answer does not exist with bow, then there's no point in keeping it, right? If this has not resulted in an answer for you, let's assume that ka will lead to bow, right? Correct? This is a better answer for you than this.
Ka cannot lead to both. Okay.
Yeah, CAW can become BOW, right?
Mm-hmm.
Oh, sorry.
Correct.
No.
Sorry.
BAW.
Thank you. To bow.
Yeah.
Right? Thank you. So if you have an answer which is like cow, bow, something, okay, a cow, bow, bought, bat, right? Something like that. And then you have a cow, caw, bow, bow, something. Then this answer is better because it's shorter. So you can actually say that this bow does not even exist at this point of time. Don't let it be a neighbor. It doesn't matter. Because you have already found the answer from this. There is no benefit for you to have this.
I think instead of going through this 25, all possible things, I think we can go by the previous definition where we will iterate through dictionary, but once we iterate through it, we remove it. Then without constructing the graph, that would be ideal fastest solution.
The first one will be, but it's essentially every loop is a n minus 1,
but we are
n
keep
minus 2, n minus
reducing
3.
it. So even if it is say 5-letter word, it is fine because we are keep reducing the dictionary. So once we process the cow, we just remove it with all the possible things. Then once we process its neighbor, we remove that.
So the crux of the logic remains the same.
Yeah.
I think you probably have to think through which one's actually more effective. I've seen both options be used. You can actually write one where you're just like looking at processing the dictionary to find the neighbors. In certain interviews, I've seen the interviewer will actually say, you know what, get neighbors function is given to you.
Okay.
Solve the problem for me.
I see.
Then it's like a very simple problem, right? Then it's like
Graph.
just a breadth first search. You just get neighbors, iterate, put to everything, put it in the queue, and call it a day. That becomes a very simple queue question.
And with some known algorithm, explaining also easy, right?
Yeah.
If we breadth first search, then we don't need to explain anything to
BFS is nothing to explain.
Yeah.
Like this is it. It's a graph BFS. You're done, and that's about it.
Even
How do
like-
you find the neighbors is a challenge.
Yeah.
You had a question.
Yeah, so defining the structure for the dictionary is done by us, or mostly the interviewer tells you that the dictionary is?
What do you expect? Do you expect the interviewer to give you the dictionary, or do you expect you to define the structure for the dictionary? I'm telling you the list of known words that is available to you.
This that we can use.
Because you may want to use a try.
So yeah, does that become part of the problem itself? Or?
Entirely up to the interviewer. So most of the problems, at the end of the day, you're trying to look for. So these questions are trying to test two things, right? It's trying to test your data structures knowledge, like what kind of data structures you want to use, and it's trying to test your problem solving ability. So once I, as an interviewer, understand that you're going somewhere with the problem solving, I want to make it more complicated because I want to differentiate between you already knowing this answer to you understanding the concept, right?
Yeah.
So what I would do is I would throw this curveball saying, you know what, now it's more. Now it's like crow, and whatever is possible. Now what do you do, right? If you're over smart and you've come back and said, you know, I can just pre-filter my dictionary to only keep the 3-letter words because that's what makes sense. Now that I have introduced this, I'm expecting you to go back and say, you know what, now I can't pre-filter anymore. So you need to keep track of that. Like all the optimizations you've made, everything is now back on the table. And that this mimics a real world problem because you're solving with constraints. And if the constraints are eliminated, you're expected to go back and re-examine each one of your assumptions, see which ones have been invalidated because of the modified constraints, and then go back and solve for it. The interviewer will help you with this, but the expectation is that you do it yourself. Okay. Anyone has actually seen a different variation of this problem or this problem in different forms? Not really.